Alright, this is going to be just a short demonstration of a program running on the Arduino, written in AVR assembly. I'm going to be showing an example of it in C++. That's kind of just a mock-up pseudocode example. I've got the circuit running here. I'm going to reset it. It's going to blink 3 times, which is the startup blink count for the LED here, this green LED, and then I'll use the buttons here for incrementing and decrementing how many times it blinks each blink cycle. So I'm going to do a reset, and after it resets it'll go through a startup blink cycle of 3 blinks. I've got a button over here connected here into port D pin 2, which is also external interrupt 0, and then a button here in pull-up mode coming into port D pin 3, which is interrupt 1. If I hit the one on interrupt 0 or port D pin 2, I now get 4 blinks. If I hit it again, I should get 5. If I hit it again, I should get 6. I can then start to decrement. That should go 5, and then 4, or that's 5. There's 3, there's 2, there's 1, and then it shouldn't let me go any lower than 1. If I hit the increment again, I should get 2, and I can drive that up, I think, till 10. Alright, so just general circuit. This button is in high impedance. We have this 5 volts from the external 5 volt pin running to one side of the button, and then on the other side of the button we have a data wire going into port D pin 2, and then we have a pull down resistor here in between the wire going to the ground rail, which is connecting here across this ground rail to this wire running to a ground on the Arduino over here. We then have this button here, which is my decrement button in pull-up mode. We have a data wire here, this orange wire, going to port D pin 3, and we have this wire, this black wire here on the other side of the button to the ground rail right here. So high impedance, pull up, and then our LED over here is connected to this green wire, which is going into port B pin 2, and then we have a 220 ohm resistor connecting its other side to the ground rail so that it's grounded. Okay, I've got this mock program over here on the right to show the code in C++, and then on the left here I have it in the AVR assembly, what was actually loaded onto the Arduino. So just to kind of cover some of side by side what's going on in general, this is a state-based program using hardware interrupts for buttons and for our timer. So just looking at basically what we have this set of states that the program goes through. For instance, it starts off in the wait input state, and then when actually at the very beginning it changes it to start blink, so that it'll go through a blink cycle, and then it goes back to wait input at the end of that cycle. And then when a button is pressed, it'll switch it back to start blink. And then what start blink does is initially, after getting the blink cycle set up, configured, we'll go through that in a second, it changes the state to blink on. And then blink on will last for the length of time that the LED is lit, and then that'll toggle to blink off. And blink off will stay the state until the for the time period that the LED is off, and then it'll switch it back to blink on. And each time it comes to blink off, it'll see, have I blinked the number of times that our blink counter has? If so, it'll change the state back to wait input, to wait for the user to hit a button again. So those are our overall states. So I have them set up here as an enum. We'll see how I did that over here in the assembly here in a second. That being said, I have some constants for the program, how long the timer will run. I used, I believe, timer 0 here, so it's a very small timer. So the most I could get was 10 milliseconds. So we'll look at the configuration just briefly. This is not about how to set up the timer, but here we have the timer running for 10 milliseconds. So the desired value we needed to put in the timer counter was 155. We want the LED to be lit and off for longer than 10 milliseconds, or we wouldn't be able to see it. So I'm using this LED count to set how long the LED on and off cycle part of the cycles are. So 25 times 10 milliseconds gives us 2,500 milliseconds, or I'm sorry, 250 milliseconds, or a quarter of a second. So we have a quarter second on, quarter second off for a half second cycle. And then we have a button bounce, and that's how many of these 10 milliseconds we should let go after we've pressed the button before we'll let the Arduino interpret a new button press. And that's to keep us from triggering multiple button presses as we press these cheapo buttons on the breadboard, which can cause a bounce effect. And so this just sets up a little delay to keep us from interpreting a new button press. So 40 times our 10 milliseconds or 400 millisecond button bounce, or what's called a debounce. And then we have some constants for the blinking. Our starting blink rate is 3, meaning that when it first starts up, it should blink 3 times. And then as we use the buttons, we're incrementing or decrementing that 3 between a min blink and a max blink of 1 and 10. So here we just have some constant integers. We can see those same things over here in the assembly, just set up using the compiler directive equate to set up these labels for these values. Now, since the C++ is not real for the Arduino, I'm just mimicking some things like a GPIO mode of output or input, high impedance input pull-up. So we'll see how we set that up over here in the assembly real quick. We went through our states. We have a fictitious button over here in the C++, so a button would have a pin, what mode it's in, GPI mode, and then a function for pressed, which would simulate or emulate, since we're not going to run this, it just kind of represents the hardware interrupt that we're configuring over here in the assembly. Same thing with the LED, it represents a GPIO for a pin with an on and off for the LED. So once again, just have something in the C++ to kind of show relatively where that should be happening. We have our function prototypes or function declaration statements for our different functions. So if I hide the assembly right now, I don't think it's going to let me, so we'll just go with this. I can always scroll over, but we see we have these functions, and I'll wait until we get through them to kind of talk about it. I'll go ahead. This is just a fictitious to set up the timer for our 10 milliseconds, and we don't actually show that here in this code. And then These are functions that will be called for the different states. So when the state is start blink, then the start blink function is called. When it's blink on, then blink on is called. Same thing for blink off. So these are our state functions, and we'll talk about these parameters in a minute. And then for the hardware interrupts, we have an increment press, decrement press, and timer counter. And the timer counter is the one that's being triggered every 10 milliseconds, and then when somebody presses a button, the increment or decrement button functions are being called, or in this emulation. So we can kind of see the layout of the program here in main. We do our one-time configuration stuff. We start our state off as wait input, and then which really, I guess I really should have that set to start blank, to kind of more so fit in with the assembly. And so we can kind of see that here, and let me kind of catch up. So in the assembly here in this enum, we had our states. Over here in the assembly, we just have these equates to represent the different states. Every label, every name label in assembly has to be globally unique. So we do things typically to ensure that everything is unique. So here I'm adding a ST underscore in front of each state to be the state wait input and state blink, start blink. And that way, if I was to use just start blink somewhere else, maybe for a function name or something, this state label would be unique. And I just noticed an issue here. This should be a different value. And I was just messing with that recently, so that may have messed things up, but hopefully not. All right, and then we have our we covered this. These are fictitious. And we looked at our functions here, and then as we get into main, we started our state as start blink. And we can see that down here in this main. Here we're starting state as wait input, but then calling this start blink function. So we'll kind of look at that and see how that works. And then here we have, so this is the blink count variable, and it starts out as start blink. And so here in the assembly, we define these variables that we're going to use, and we see them all here in this main here. Here we're setting them up as global because we don't really have this concept of being able to pass them to functions. There is a way to mimic that by putting things onto the stack. I forgot I changed this to camel case. That's why it's showing red right now. But so here though, these variables, we're just allocating a label to a particular address in our internal SRAM as to where we would store. So each one of these is a 1-byte variable stored at these individual addresses. So here we have our state variable at address 0100 in hex, and here we have our state variable being declared in the C++. So our blink count for the number of on-off cycles we should have, so 3 would be 3 on and 3 off, so that we get 3 total blinks. So we have that here. And if I jump down to the start blank, we can kind of see how that gets set. Actually, I think we have a start blink in here also, so it's kind of the same thing, and I could have set up the C++ to show that we were calling start blank and not having to do it here as well. So let me just kind of stay here with Here we're setting our blink counter. So blink counter will just be a copy of blink count when we're doing an actual blink cycle. We'll copy the current blink count into the counter, and that way we can decrement this counter till 0, and we're not modifying our state variable blink count for how many blinks each cycle is going to be. And then we have an LED timer. This is really just a counter variable. We see that here, and that's for counting how many of the 10 millisecond timers have gone by. So we're going to count down to 25 to get a full quarter-second delay. And then we have a button bounce counter, which here is just being called button timer. Here it's button bounce. And so we're starting out as 0 until a button is pressed. We also have this timer flag. The timer flag is declared here, representing a Boolean. And the timer flag just tells us that a 10 millisecond timer has expired, and so we can look to do things. So we'll only do stuff on those every 10 millisecond intervals. Here over in the assembly, I'm going to be using R16, register R16 as a temporary variable throughout the program, and R17 as a temporary state variable. And so these are going to be used through any of the different functions. And so here I'm just giving them labels and predefining which GPR register they would be in. Now over here in the assembly, we have to set up the vector table. So this is our first actual executable code. And at our reset vector address 0, we have our jump to main, which would take us to this LDI. And then we have for external interrupt 0, we have a jump to a button up interrupt service routine. And for interrupt 1, same thing for our down ISR. So this would increment up, increment down our button count. And then we're running our timer in output compare match or CTC mode. And so here, every time it throws its interrupt, we jump to this timer 0 interrupt service routine. All right, and that ends our vector table. And so we start with our main where we're duplicating. Here we are using, I could have used the temp label for these R16s, but here I'm starting it off as weight input, and then I'm putting a weight input into a GPR. This is just a constant defined up here as the state, so the value 1. So I'm putting a 1 into R16 and then storing R16 to the address for the state variable, so 0, 100. All right, and so that'll be very similar process going forward. Blink count to store the initial 3, which I could have used this start blink constant here for that. And that just allows us to easily configure for the next run if we want that to be something different. It's easier to open up the program, change that 3 here, and not have to worry where all start blink is at. So we're putting that, storing that initial value in the blink count variable address. So I'm going to stop going back up for this, but here we can see that's address 101. And then now we're going to call this GPIO setup function. Over in the C++, we're kind of doing that here. So instead of having a function for it, I have this fictitious LED variable, which is of type LED, which is this structure I created here. And so we're setting the pin 10. And then for our button increment, button decrement, we're setting those pins. And so here in the assembly, if we go to the GPIO setup, we can see we are configuring on port B, pin 2, we're putting a 1, so we're making that output mode in the data direction register for the LED. Here for input for the button up pin, which I defined as a constant up here, button up as pin D2. So I'm going to stop going up to find those labels now, but here in the GPIO setup, so we're clearing the direction register for that pin to put it in input mode, and clearing the output register for that pin to make sure it's in high impedance mode. We're then registering interrupt 0 in the external interrupt mask register to enable the interrupt, and I'm setting it R20. I'm initializing to the rising edge trigger for interrupt 0, which I just kind of set up here as a little equate. So put a 1 in this pin number and a 1 in this pin number. And notice that's just being stored in R20 for right now. And then for the button down, we configure it as a 0 in the direction so that it's in input mode, and then a 1 in the output register to pull it up high as a pull up. We register interrupt 1 in the mask register for it, so remember the SBI functions just modify the 1 bit. And then for the R20, we OR to it this interrupt 1 falling, which is for the pull-up circuit. Interrupt 1 fall is putting a 1 in this pin and a 0 in this pin. And so that value there is being, this value here is being ORed with this value so that we're getting basically the combination of those 4 bits set in R20, and then we store R20 to the control register for the external interrupts, which is not an internal I/O, so we have to store it to using the STS instruction, which updates all 8 bits. And so that's our GPIO setup. And then our next function call in main calls the timer setup. So just briefly, the timer is set up here. The counter register is set to 0 by clearing it, and then the control register A, or the output compare match A, is where we put our timer count value, which was 155 for the 10 millisecond delay. So that it'll count from 0 up till it matches the timer count in the compare match register. We're putting it in CTC mode, so remember this is timer 0, so we're modifying the A register for this wave generation mode bit based off the table, configuration table for timer 0, and we're putting the clock prescaler 1024 into the B register to start the timer, and then registering for the output compare interrupt enable for the A side in the mask register for timer 0. So that's our timer 0 setup. Coming back up into main, we now call this F start blink, and this is just a function, and it's similar here, that anytime we need to reset to start a new blink cycle, we call this function. So the buttons call this function. So I'm just calling it here from the configuration in the assembly to not have to rewrite those instructions. So here we can see in the assembly F start blink versus the C++. So in the C++, we need to put count, which is the current blink count, which starts out at 3, into the blink counter register. So I just slightly renamed them to make them briefer here in the methods. Over here in the assembly, we can kind of see that. Now notice we're going to be using R16 throughout here. So we're saving whatever current value might be in R16 and then restoring it at the end of the function. So we'll see that in all the functions. But here we load that blink count, which was 3 to start with, into this temp GPR register, and then use that to store that value to the blink counter. So that is just the counter equals the count. So this counter now equals or has a copy of the value that started in count. Here I'm using this reset timer because I have to do this several times, which calls this function here, which once again uses R16, so it saves it and restores it. But all it does is take the hard-coded constant LED count and store it to the LED timer variable, which we see here as well in the C++. And then here back in fstart blink, we then take the state constant st blink on and we store that to the state variable, which is kind of illustrative of these all being returned and or parameters that are modified and a return. Here we see parameters that are being modified using reference, and then the return type, which is what's being returned from C++. So here we're kind of doing that in the assembly just by storing it to the global state variable. Right, so that is our fstart blink. If we come back up to the main configuration area, that gets our cycle ready to go for the first blink, and then we enable global interrupts. So then we enter into the main loop area, and back over here we have our while true, which is the main loop in the C++. So just kind of looking through the C++, these are not not this way in the assembly because there are hardware interrupts that are triggering calls to these functions directly. In the C++, I'm kind of just emulating them here to kind of show our timer counter function is going to set a timer flag. Increment press and decrement press are going to set the state variable. All right, so we don't really see that here in main loop, and we'll look at those individual functions to see how those work. But we can see this if timer flag. So here in main loop, the first thing we do is load the value in the timer flag from memory, from internal memory to a GPR, and then test it to see if it's 0. So 0 would be false. And if it's 0, a test will set the Z flag on. So here we're doing a branch equal, meaning if the Z flag is set, we can jump to main. So if this is false, we can jump to main. Or we can kind of reword that to say, if timer flag, then we're going to come in and do this, else we're going to continue around this loop. In other words, we're going to skip all of this. Over here in the C++, we see that as if timer flag is true, do this, otherwise skip to this ending curly brace, which hits the ending main loop, which brings us back up to the top again. So we're kind of flipping that a little bit in assembly because our branching instructions, we need to skip stuff, whereas our conditionals here are to go into the block. So that's our, so this here represents just this if statement. And then here we have our case statement. So our switch case statement. So we're loading the state memory, the value at state, the global state variable memory into our temp register, just like here we're doing a switch state. And then here, each of these case start blinks are really a compare of what came in from state into temp against these state labels. And so if this equals that, or the Z flag is set by subtracting this value from that, and that results in 0 setting the Z flag, then we branch equal to this label here, which represents the code of the case statement. So if state equals start blank, we jump down here and we call fstart blank, which we see here. Now here in the C++, we're showing we pass these variables, but in the assembly, all those variables are global, so we just rely on the fact that start blank can see. But here we have a break, and here we just jump to the end case label, which is down here. So we do the same thing for here, blink on. So if our state is blink on, then jump to case blink on, which calls F blink on here, and then breaks, which is the R jump to end case. And then we have case blink off here, jump to blink off, which calls F blink off here. And so we see that here. And then notice after the return from blink off, this would fall through. And so we see that same setup here where we don't have an R jump because we're just going to, if we end up at this label, we are going to end up after the call going to this anyway. And so here we can see in the C++, we're just setting timer flag to false. So over here, we're clearing our temp register and storing it to the timer flag memory to set that variable to false. Then we hit our end main with our R jump back to our main loop, which we see here after we come out of the switch case statement, or here this is the if timer flag is true, then go back to main loop, which is here. All right, so what we can kind of see is in the C++, if we get the timer flag set to true by the timer, meaning 10 milliseconds has gone by, then we come in and we see, well, what state is the program in? If it's blink, start a blink, then it calls this to reinitialize the blink. When that returns, this state should have been modified to blink on, so that as we come back from this, we break down here, we turn that timer flag off, and then we come back around, which means we're going to wait another 10 milliseconds to come back in and find out that our new state is blink on. And so there we would call blink on, and it will return probably blink on until 10 milliseconds is gone, or until a quarter second, 25 times 10 milliseconds has gone by. So we'll see how that works here. All right, so let's follow some of these. We've kind of already looked at start blink. Just to review again, all it does is set up the counters for the next blink cycle and sets the state to blink on. All right, and so we saw that here in this program as well. So start blink sets up the counters and then makes the state blink on. And then here, if we go to blink on, we can see, let me scroll here to blink on. So here, blink on is going to use two local variables, return state and temp, as GPR registers, so it saves their values. And notice it has to pop them in the exact opposite order. So push return state on the stack first, then temp, which is now sitting on top of return state. So it must pop temp first and then return state before hitting the return. All right, so here in blink on, we start out by setting return state to blink on. So we're assuming that for a bunch of times we come in here, about 24 out of 25 times, the timer is not going to be at 25 times our 10 millisecond counter, and so it'll need to keep going back around again. And so it just keeps the state as blink on. So we see that here as well. We start out by setting this return state, which represents this local variable, this time in R17. We set it to blink on. And then we just assume every time that we come into the on cycle, we're going to turn the LED on. So we see that kind of mimicked over here in the C++, but here we use our SPI to turn it on. And then we here we check if the timer is 0, so we need to first load that into our temporary register from its state from its variable memory address, and then we can test it to see if it's 0. So we're basically saying here, if it's 0, then we can reset the LED timer and start with a blink off state. So we see that here. Here we're, otherwise, if it was greater than 0, we would end up down here, and we wouldn't. We'd still be on blink on, and the LED would still be on. So we see that mimicked here. we test for 0. If it's greater than 0, then we don't go in to do this, so we're doing a branch not equal. So if it's not 0, we're going to branch to blink on return, which is the same as coming down past this curly brace. Otherwise, it is 0, and so we're going to reset our timer and then change the state to the return state here to blink off, the local return state variable, which we see here. And then we would come through here, and we're going to put that return state into our global state variable, which is like returning that return state, since up here we have state equals. So we're just doing that right here. And then in our function, here we go ahead and restore our temporary registers and do our return. All right, and so blink off is going to be very similar. Here we have blink off at the C++ level, and if we just read through that real quick, we're going to initialize this local return state to blink off, meaning we assume we're going to stay in blink off for a quarter of a second. And so every time we're going to turn the LED off and then wait for that timer counter to get set to 0, meaning we went 25 times or 25 10 milliseconds. And so there, here, when we do have an off cycle, that means we've done one full blink. So we're using this counter here as the blink counter. We copied the original blink count into this counter. So if it was 3, we would now be decrementing it to 2. And as long as that's greater than 0, then we just reset the timer counter for the LED and set it back to blink on, meaning we need to do another blink. If it does get to 0, that means we've done the full number of blinks for this cycle, and so we change the state back to wait for input. So we see that over here in the assembly. We start our return state as blink off. We then clear the output register for the LED pin to turn the LED off, and then we load the timer counter. So here where we're doing this if test, and we test that. If it's not 0, that means it's greater than 0. We don't need to do any of this stuff, so we go ahead and jump down to off return, which is just going to return the current local return state, which was blink off. All right, so we see that here. Otherwise, if it is 0 here, if it would have been equal, then we would not branch, so we fall in here. And so we start by loading the blink counter and decrementing it, and then storing it back to its variable. So that's the same as counter minus minus right here. And then if that got set to 0, then a branch equal will branch, because the Z flag would be true after this decrement. So this is, if the counter is 0, we're going to jump to this else. So the opposite of the greater than here, which would allow us to fall in. So if it's not 0, then that means we need to reset the timer, which is our little local function that does that step. So just to kind of show again, that's this. All this does is reset the counter to the, that should not be timer count, that should be LED count here. But this is just a fake program, but I was trying to set it up to be as close as I could. But we want that to be the 25 times that we are going to run 10 milliseconds, not the 155. So we're going to blink off. So we called f reset timer from the blink off function. And then we put blink on as the new return state to start the next on cycle, since we have not reached the blink counter. If we load blink counter and we decrement it to 0, then that means we blinked it however many our blink count was originally for, say 3 times. So we've had 3 on-off cycles. And so here, when we decrement it, temp will be 0. Branch equal will branch to reset here, which would put wait input into the return state. So if it wasn't 0, we came in, reset the timer, made the return state blink on, and then here we're skipping this reset to get down here. So either way, we either reset the timer, set the new return state to blink on, and then copy that into the state by skipping this and then return, or when we decrement the blink counter, it is 0, and so we branch past this code to set wait input into the return state, and leaving the timers and the counters set to 0 since they got decremented to 0 to get here. All right, so you can kind of see how this code is mimicked in the assembly, or would be compiled down to the assembly here. All right, so the only things we have left, we talked through the timer setup. Here we have our button up interrupt service routine that's called by the interrupt, the hardware interrupt. So here we can see in the C++, we assume that we're going to return wait input from increment press, and we look here to see if the button was pressed. This is fictitious because our assembly auto-magically calls this when a button is pressed. So that's what this represents. All right, but we see here in the C++ when we do get a press, the very first thing we do is just check to see, is there a debounce timer running, a counter running? In other words, if our parameter debounce is some number greater than 0, which was originally, I believe, 40 to get 400 milliseconds, then we don't want to interpret this button bounce as an increment. We want to wait for that 400 milliseconds to go by before we'd interpret a new button press. And so if it is greater than 0, we're just decrementing that debounce counter. Otherwise, if it is 0, that means this is a new press. So we check our counter, which is the button count. We check to see if that is less than our max blink. If it is, we increment it, and then we change our state to start blink to start a new cycle, and that's what would get returned. So we're returning wait input if there is a button debounce happening. Otherwise, we would end up returning start blink because we've incremented the counter. So decrement works the same way. It's just the opposite. We're still checking a debounce to make sure there's not a debounce running. If it is, we make sure the counter is greater than min. We decrement it and then return that new start blink state. All right, so we see that over here in the button increment. We see we start out by saving these local registers that we're going to use, and then we put wait input into the return state, and then we load the button bounce in and test it. Here, if it's not 0, we just jump to button return, where we end up returning the wait input. If it is 0, a branch equal scenario, then we don't branch, and we load button bounce, then the original button bounce, we reset that into the button bounce variable because we have just triggered a button and we need to have a button debounce counter going. So we go ahead and initialize button bounce to that. And then we set the, which I didn't really show here, I should have shown that in the C++. I'll go ahead and add that. So that would be debounce equals button bounce. Okay, and then let me go ahead so I don't forget to do that later. When I talk about it later, let me go ahead and mimic that down here as well. All right, so that means we've started a new button press, so we need to start the bounce counter again. And then So then after that, we then go ahead and we load our blink count into a temporary register. We compare that against max blink. So if it's less than max blink, so since we want less than, we branch if same or higher to button up blink, which is here. In other words, we don't increment. But if it isn't same or higher, then we increment that temp register, which is blink count, and then store it back to the blink count variable memory. And then we would fall through here. Either way, as we see here, we end up putting start blink into this. So this code here represents this if statement here. So if counter is less than max blink, we can increment counter. So that is this code here. And then either way, we're actually that includes this. So that is this 2 lines here. And then either way, we're going to put start blank into our return state for the return. All right, so that's button up, and then button down is going to look very much exactly the same. The only difference here, we have the button bounce being tested if there is a button bounce. So if it is 0 or if it's not 0, we skip down to button return, where we're going to return wait input because there's a bounce happening. And otherwise it is 0, and so we come in and reset the button bounce for this new button press. We test blink count by loading it and testing it against the min blink. And then here we need a less than or equal to skip this. In other words, we want it to be greater than min blink to come in here and decrement it. So if it's lower or the same, then we don't want to decrement. So we do a branch low or a branch equal down to button down blink to skip the decrement. So here we're doing the exact opposite of the greater than to set a less than or equal to condition to skip the decrement counter. So if it is greater, it's not less, it's not equal, we decrement it and store it into the blink count variable. And then either way, we put start blink into return state and return it. All right, so that is the program. So I hope you can find some help in here to help you with your final projects on some ideas on how to run different things like state-based programming, scanning, and not having blocking delays so that you can still capture button inputs and control LED blinking while other things are happening. And then also how to set up if statements and loops and functions and things like that.